This is Math 251, section 14.5, and we'll talk about two concepts, divergence and curl. We kind of teased these concepts a little bit in the last section. We've already looked a little bit at what divergence and curl, or where they occur in Green's theorem. But I'd like to back off a little bit and talk about them a little bit more formally, as well as how we might interpret them, and maybe it'll make Green's theorem make a little bit more sense to us at the same time. So in this section, we're going to actually define our divergence and curl using the concept of the gradient as what's called a differential operator, or sometimes the del operator. Remember that if we've got a function f of x, y, and z, we define the gradient of f as the vector, partial derivative of f with respect to x, and then with respect to y, and then with respect to z. We can think of that gradient as essentially a mathematical operation that says, take the derivative of whatever with respect to x, then y, then z. By itself, we could write the gradient operator this way. Now notice, it is just an operator. This in and of itself is meaningless, just the same way as that radical is meaningless, or a plus sign or an integral are meaningless, unless we have a function to work on, right? These all give us instructions for an operation to perform, but nothing on which to perform it. However, we do use it as a useful symbol for a mathematical operation, and we're going to see exactly how we do that as we define our divergence and curl. So let's start with divergence. The divergence of a vector field f, div f, is defined as the del operator dot product with the vector field f. In two dimensions, that would look like the vector field fg, and div f would be our two-dimensional gradient, partial with respect to x, partial with respect to y, dot product with f, which is fg. We'll do our dot product the same way we always do. The first, so partial f, partial x. And then remember it's plus, right? Dot product is a scalar, so we add partial g, partial y. So notice the divergence just ends up being that scalar quantity, and you probably recognize that as the scalar quantity that was part of Green's theorem in its flux form, that two-dimensional divergence that we mentioned in the last section. Now that we've got this definition, we could actually define a three-dimensional divergence as well. If f is fgh in 3 dimensions, then div f would be the three-dimensional divergence operator, dot product with fgh, and the divergence then will come to be the partial of f with respect to x plus the partial of g with respect to y plus the partial of h with respect to z. You can easily see how this could go on into as many dimensions as you wanted to, although for all practical purposes, 3 dimensions is usually sufficient in our three-dimensional world. All right, keep in mind, what did the fact that divergence of f equals 0 tell us in the last section, the two-dimensional case? Well, it told us several things, right? If the divergence was 0, then the flux was 0 on a closed curve. And it also told us we had a source-free vector field f. So, two interesting and useful things to know just by the fact that the divergence of f was 0. At this point, we can expand that and say, well, if that worked in 2 dimensions, now that we have a 3-dimensional version of the divergence, that should work for any number of dimensions, including 3. So, if the divergence of f is 0, no matter how many dimensions we're working in, then f is source-free, and the flux is 0 on any closed path C. All right, just for a little practice, let's calculate a few divergences. Here's a vector field where each component is just linear. So we're going to calculate the divergence, and then we'll decide whether or not the vector field is source-free, keeping in mind that if we get 0 for the divergence, that's the determining condition that makes f source-free. So divergence of f I'm just going to go ahead and write out the del operator. Oops, that's a z. Dot product with this vector f. And so in the first components, I take the derivative of the first component with respect to x, and that's just going to give me 8. Plus the second component gets taken the derivative with respect to y, giving me -2. And the third component, the derivative with respect to z, -6. Adding those all together, I do get 0. So in this case, f is source-free. All right, let's do a couple more. In B, divergence of f, and again, I'm just going to go ahead and write out my del operator. Dot product with the vector field f that we were given. We do our usual dot product structure. We take the firsts. Derivative with respect to x would be a -1 e to the minus x plus y. Plus the second one would be a -1 e to the minus y plus c. Plus the third one, which again chain rule will give me -1 e to the minus z plus x. Now those are not like terms, so I can't combine them. That's not uniquely equal to 0. And I'm going to have to say that's the divergence. So I do have a divergence, just like the divergence here was 0. But f is not source-free. All right, one more. Divergence of f, my del operator, dot product with the new vector field, and let's see here, with respect to x, we're going to get a 2x times the constants yz. Plus here, we have a constant multiplier of -2x times the derivative of y squared is 2y times the constant z. Plus, taking the derivative of the last component with respect to z, I've got the constant multiplier xy times the derivative of z squared is 2z. So we have 2xyz minus 4xyz plus 2xyz, which does add up to 0, meaning f is source-free. All right, so that's basically just mechanics of calculating the divergence, and then the relationship between divergence and being source-free. What I'd like to do is talk about the divergence a little bit more geometrically, which is what we'll do in the next page in the next example. So if we evaluate the divergence of f, particularly if it's not just 0, and we can actually plug points into it. So for example, when you think about this one that didn't turn out to just be 0, I could have taken a particular point, 1, 1, 1 or something, and plugged in the x, y, and z values, and come up with a value for the divergence of f at that particular point. What does that mean? Well, if we evaluate divergence of f at a particular point, it measures the amount of expansion if we have positive divergence, or contraction if we have negative divergence, that is experiencing, or the vector field is experiencing. To see this visually, I'm going to consider this vector field f, which is x squared y, and I've got the picture drawn here for you. Would the divergence be positive or negative at the 2 points P, negative 1, 1? You'll have to put that one in yourself. That wasn't in the original diagram. And then Q, 1, 1. All right. Well, what you want to imagine is think about P here. And if you're moving with the vector field, so I'm kind of coming from the left and moving toward the right, just imagine kind of being carried along by that vector field, almost as if it's like a velocity field and it's like current in the water carrying you along. What I'm hoping you're seeing is that as you move through P, the magnitude of the vectors is actually getting smaller, right? We had a larger vector here, a little shorter here, and a little shorter yet here. So the vectors are decreasing in magnitude. We think of that as the vector field contracting. Again, if this was a velocity field, you might be having your water moving fast here, slower there, and even slower over here. If this field represents gravitational pull, there's a strong gravitational pull here, less here, and even less there. So F is contracting, meaning the divergence of F is negative at the point P. All right, what about Q, the point 1, 1? Again, imagine moving through this point Q, following the vector field. So from the left, you come through Q, and you're going to keep on kind of going out this way. We have a very small vector over here, growing to a little bit larger vector there, and an even longer vector out here. So here I'm going to say the vector field is expanding. The magnitudes of the vectors are getting larger as we move through Q. So again, we say F is expanding. And when that happens, the divergence of F should be positive. All right, so having made those predictions based on the geometry, let's actually calculate the divergence for that vector field. And we'll plug in the values for P and Q, the X and the Y, and figure out if we do get a negative divergence at P and a positive one at Q. So divergence of F is our del operator. It's just two-dimensional this time. Dot product with the vector field. And that's going to give me 2x plus just 1. So at the point P, which is what, negative 1, 1? The divergence would be 2 times the x value, which is negative 1, plus 1, or negative 1. Notice we predicted it would be less than 0, and it is less than 0. Vector field was contracting. That's what should be happening. At Q, which is 1, 1, the divergence of F would be 2 times 1 plus 1, would be 3. Notice we predicted it would be greater than 0 because the vector field was expanding, and that's exactly what happened. So it seems to be making a reasonable prediction, telling us about the contraction or expansion of our vector fields. One last thing, it says, determine the conditions under which the field is expanding and contracting. So we know the field should be expanding when the divergence is positive. Divergence we already calculated was 2x plus 1. So the condition for expanding is that 2x plus 1 is greater than 0. Or in other words, x is greater than negative 1/2. Of course, exactly the opposite for contracting, but I'll write it out anyway. The condition for contracting is the divergence of f is less than 0, negative, and my divergence is 2x plus 1 for this vector field. So that would give me x is less than negative 1/2. It was given away just a little bit in the diagram, but if you go over here, back up to the diagram, x equals negative 1/2 is actually this dotted line right here. Just make that a little bit more obvious. And everything on the left side of that vertical line, x equals negative 1/2, we're seeing a contraction of the vector field. The vectors are getting smaller in magnitude as we move toward that vertical line. Everything on the right of the vertical line, the vectors are getting larger as we move away from the vertical line. The vector field is expanding. All right, so that's a nice visual example of what we see when we're calculating divergence. All right, I'd like to do one more divergence example before we turn to curl. This time we have a rotational field. F is minus y, x minus z, y. We want to calculate divergence and discuss why it makes sense, given the geometry of the field. So let's calculate first, and then we'll come back to this idea of the rotational field in 3 dimensions. So I'll use my 3-dimensional del operator. And let's see. Derivative here with respect to x is going to be 0. Plus, here with respect to y is also 0. There's no y's in that middle component. And the derivative of y with respect to z is 0 once more. So we have a divergence of 0. This means that I do have a source-free vector field. So what's going on here? Let's compare the case of the non-source-free and the source-free vector field. If we go back to this one, which did not give us a divergence of 0 in general, we have a vector field that's not source-free. In order for the vector field to contract, the material that crosses over here must have somewhere to go. We often call that a sink. And in order for it to expand on this side, we must be creating material kind of on this vertical line. And that material is spreading to the right. So there's a sink coming in from the left, and then a new source going out to the right. That vector field has a source. It's not source-free. Compare that to this one. This is just a rotational field. We've seen rotational fields in 2 dimensions. This is simply a 3-dimensional one. And if you think about what happens here, right, they kind of go around like this. That's just a quick 2-dimensional diagram. But the size of the vectors doesn't change along that kind of circular path. No material is being created or destroyed. I have neither a source nor a sink. My vector field is source-free. All right, that brings us to the end of our discussion on divergence. We'll talk about curl in the next video.